but 3 years ago, in the Bangkok. I've been there, but I didn't remember that I listened this paper because at that time I was focused on the VR, so I probably not listened this. But yeah, the authors, I would like to introduce some authors. This name, I've been reading a lot paper from his papers. He's a professor in a Laval University, which is Momo's provider now. And these people are Adobe researchers. So this paper was researched based on the Adobe project. And then the reason why I'm presenting this paper is my master thesis is going to be lighting estimation. And then this paper gave me a lot of inspirations. So I'm going to present about it. For rendering synthetic object in a real world, the illumination is the key. You see the worst image, you see the best image. You see like this, it's really obvious. You can see the really bad rendered. But in this scene, in this image, which one do you think is synthetic object? Which one? Blue bowl, and then? Yeah, actually this was a synthetic object. It looks realistic. So to do this, the current approaches and limitations, there's a lot of limitations right now. To get the illumination to render perfectly, you have to calibrate the camera and you have to set the chrome ball to get all the lights, locations and everything, intensity, and also specialized hardware. You cannot get the illumination information by using your phone. It's really hard working. And yeah, scene knowledge, which is like you have to know the, you have to reconstruct the scene geometry to get a geometry information. But in this paper, they try to not using all these stuff. Like they're gonna make it simple with using deep learning. So the goal of this paper is given a single indoor LDR image, which is like low dynamic range image, recover a whole HDR environment map. HDR is a high dynamic range image, which contains the intensity of the light and everything. So if you have an HDR environment map, you can render synthetic object based on that environment map. So this is an overview of the method. You see the panoramic image. This is HDR panoramic image. And they crop the image like just like you take the picture. If you say you took a picture in this place and you see the crop image and they use this for input image and they want to get estimated the light. They using CNN. To train their network, they used a lot of panoramic data. Firstly, to train network with panoramic data set, they used a LDR panorama data set. In case of using HDR, it contains illumination information already in the image, but not LDR. So like LDR could be any kind of image, like JPG or GIF or like PNG. So they used these techniques to estimate light from LDR image. I'm gonna describe like briefly because like these are, you see the descriptions. It's very briefly described. They used HOG first, a feature descriptor. So like the Professor Lalonde, he's been working on classification, like leveling the image segmentation a lot. So he knows a lot method how to use this kind of stuff. So to get the light in from the LDR image, he used feature descriptor and supervised learning models that analyze data used to classification and regression analysis called SVM, and also a technique for multi-class image segmentation and leveling called CRF to get the light. And from that, they created light classification, which is the subtitle of this section. Also, finally, using thresholding to obtain a binary mask. Using light classification, they estimated light, and only to get light mask. If you after using light classification, they could level 4 types of lights in the image: spotlights, lamps, windows, reflections. But they use classification only to get light mask, which is the right one, this. So they didn't use leveled light for any special purpose. Nah. Those 3 rows just showing that they used this data to classify the lights, and they found the lights here, and they got a light mask. That's all. They didn't use any special purpose for different data. From this data, they detected light, and they got a light mask. Yes, different examples. And yeah, they manually annotated the lights, labeled the lights, a set of 400 panoramas, manually. Seriously. I was like, oh my gosh, really? I respect them. And then they trained the classifiers. So now they got really good results by using their lights classification. No. They just use to get the lights, but they also label the lights at the same time. But they're not using labeled lights for special purpose. I was like, why? It's kind of waste. Why don't you use it? But I don't know. The next one is warping operator. It's the main title. If you see the main title, it's called Panorama Recentering Wrap. Yeah, I'm going to explain about it. The aim of the warping operator is to generate the panorama that would be captured by a virtual camera placed at a point in the cropped photo. Because they want to get an environment map based on using cropped image as input. So, let's see. But however, this is a challenging problem that is made especially harder by the fact that we do not know the scene geometry. And so, they made 2 assumptions to make this task feasibly. The first assumption is the panorama scene lies on a sphere, and which means all scene points are equidistant from the original center of projection. And the second assumption is image warping suffices to model the effect of moving the camera. Means occlusions are not an important factor, and this is, if you see the video, it's well representing, you get the idea. And they use these equations. So the aim of the warp operator is create a virtual camera of the projection with a neither at an angular distance of beta with respect to the original neither, the beta. So you see if you like imagine that camera is located in the center of the sphere, and you want to get the close, like you want to move the camera to get more close captured image. So like, yeah, it's pretty simple equation if you know the 3D sphere equations, and solving this equation for t maps the coordinates from the original environment map to the ones in the warped camera coordinate system. VXYZ is virtual camera's coordinates, and this is the angle that you want to move the camera, and that's what I understood. T is the unknown value. So they want to you like it the sorry, I yeah. T was I am sorry, couldn't understand that. Also T. They don't understand. They don't mention it, but like solving for T says maps the coordinates from the original environment to the ones in the replica camera coordinates. I'm sorry. Yeah, I was wondering about what the T means, but they're not mentioning T any place in the section. It's I guess it's an unknown value to get the warped, recentered coordinates. I'll reply it later, I'm sorry. Okay, let's move on. So this is the result of the recentering warping operation. You see the original panorama. If you use a panoramic image as the environment map, the bunny model will light like this. Relighting with this environment map will be like this. If you like imagine that you put the bunny model at the top of this desk, but still because there's no light, like less light, so it's so dark. So the bunny looks so dark, but this is the result of the warping operation, and it looks pretty cool. And they actually capture the lighting condition on top of this desk, put the chrome ball to capture all the light conditions, and then they took a panoramic picture. So this is like ground truth. So compare with the ground truth, looks really close. Imagine that you wrap this environment map to the sphere. Yeah, this one. Then you see the lights on top of the image. That's like relighting the bunny. Well. I explained it at the beginning, but like because since they are using cropped image as an input to get the perfect environment map, in this panoramic data, they crop the picture here and put the network, and network generated this. then it's totally wrong, right? That's, yeah, yes. Mm-hmm. Yeah, yeah. But the network trained by panoramic data, and you put the crop image as an input, and network generate the panoramic data. In case of this, they cropped this, and the network found the perfect panoramic data, which is this one, and generated this light, which is totally wrong. Um, they just they didn't consider about that way. They just like considered they would rather like you know to like annotate all information in the panoramic data. They rather using wrapping operator to generate a similar look kind of panoramic image. So if you see this picture, it looks not well panoramic data, but they wrapped, like they 확대 zoom in the panoramic data to get the perfect lighting conditions. Yeah, I know it's kind of confusing. Yeah, I was like, huh? mm. Mm-hmm. Mm. Mm. Network has a wrapping operator inside. So the network can do, yeah, network automatically recenter the panoramic image to get the perfect lighting conditions. Yes, it's crop the image. Yes. Ah, sorry, I shouldn't say network. If you just wrap this as an environment map and relighting with this, you will get this result. So I don't know where did um, so yeah, even if the network has this data, it's not the perfect environment map to generate. So they like have a function of recentering the panoramic data since they're using cropped image at the center. I thought I explained well. No, it's. I think it's a kind of confusing. Yeah, just like you. As a, if you read this paper in this section, they explaining the aim of this warping operator a lot, like twice. It doesn't have to be, but they're explaining why we're doing this and why we need this. I think it's because the reviewer also confused about this function. But the, if I say that again, the aim of the panoramic recentering warp is to generate the panorama that would be captured by a virtual camera placed at a point in the cropped photo. That's okay. Seems like I'm not doing well. Everybody's like, still don't know. In the end, yes, yes, yes. Uh-huh. And this is also they mentioned in the paper. They since they're using cropped image as an input, they want to generate a panoramic data, the environment map, which has the the bright lights on the top to generate, to re-lighting and re-render object well. I don't know, I understood, but like, it's hard to explain. Like, imagine that you have a sphere, 3D ball in front of you, and you have a fabrics of that image. You cover the sphere with that, and you want to place the bunny at the very like far away desk here, but they took a panoramic data over there, and the light condition is totally different. Here, at the center of the panorama, it's so dark, but you place the bunny at the really bright area here on the top of the desk, then it should be different, like bright. It should be brighter. But if you use that environment map, the computer is stupid, so like they render object with dark lighting condition. Oh. Yes. Yes, Siri? Any question, Siri? Yeah? Yes. The column, yes. The first column is just normal panoramic data, and the second column is the result of wrapping operators. No network, please. Please, no network. It's just like the wrapping operator is another function in the network. It's not the output of the network. It's just the result of the wrapping operator. So, what should I do? Wrapping is you stretch the picture and cover it, or you place 합성할 때 사진을 일단 다른 사진이 있으면 거기에 맞게끔 끼워 맞추는 작업을 와이핑이라고 해. 네, 야매로 말하자면, 네, 그렇습니다. I am so sorry. I'm a terrible presenter. 네. Yes. Here. Bunny is supposed to place it here. Yeah. Because the whole sphere is covered by dark lighting condition panoramic data. That's why I was keep telling you that imagine sphere is in front of you and cover this panoramic data, wrap the sphere, and yeah, from this data, yes. No, that's totally wrong. Oh my gosh. I should have made this in the 3D scene. Oh God. Is there anybody knows IBL, image-based lighting? No. Okay. Okay. Yes. Mm-hmm. Yeah. Yes. Yes. Uh, yes. You're right. Mm-hmm. 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 Yeah. Yeah. Mm-hmm. Mm. Yeah. Yes. Was Sam's comments helpful for you, Professor? I'm so sorry. It's very easy if you imagine like you have 3D sphere and it's the material, the texture is this, just surrounded in this place. But like this place is so dark. That's why Bunny rendered dark. Okay, let's just move on. Now I'm gonna explain about the architecture of their network. Um, they used end-to-end deep neural network. First, they take a picture as input and they encode it and they decode it to get light mask and RGB panorama separately. You see the wrap, it's a wrapped. The detail about this network is like this. Encoder, they used ResNet blocks. Decoders, they used the deformed layers. No pooling, striding, Atom optimizer, 38 million parameters. A lot. And they used this loss function. I'm going to explain about their loss function. They used L2 loss on the RGB first. And you see that's a basic L2 loss function equations. And total number of elements in this image is n. N is the total number of elements in this image. And it's width times height times 3. And the Y is representing network prediction here. And the T is a ground truth panorama. And SI is a solid angle for pixel I. And they use a cross entropy on the light mask. This is a filter based on the cosine distance. The letter F represents a filter in their loss function. This one, F. And then this equation representing F, the omega I is a hemisphere centered at pixel I on the panorama P, and Ni is the same as unit normal at pixel I, and Ki is the sum of solid angles on omega I, and the this omega, yeah, small omega. So unit vector in a specific direction on big omega I, and yeah, this. And by adjusting parameter AE, I didn't explain this alpha E. This alpha E, you can get different results, and they called it is tunable render loss function. So you can get a diffuse result, you can get glossy result. Environment map also affecting on the material, the reflection of material. So that's why if you want to render the diffuse material synthetic object, then you set the alpha E as a 1. If you want to make like mirrorable or mirror something, glossy material object, you can set alpha E as a 80. Finally, this is a global loss function that combined with last loss functions. The video shows the evolution of training and test loss over the number of epoch. Oh. See again. And finally, you see the lights here. Yes, here. Ta-da, ta-da. And they mentioned that they used the W1, 2 is a weight. W1 they set it 100. The W2 they set it 1, and alpha is 3. This is a detail about the training. First, they generated the train test split network, which means no crop of the test panoramas exists in the training set, and they used 85% of the panoramas as training data and 15% as test data. All tests are performed for scenes and lighting conditions that have not been seen by the network before. And second, they used Adam optimizer, and they described more detail about using this optimizer over there. Lastly, they trained their network on the NVIDIA Titan X Pascal GPU, and it takes roughly 40 hours to train. And test time of lighting inference, both mask and RGB from a photo, takes approximately 10 milliseconds. The batch size was selected. It fills the 12 gigabyte memory of the GPU. And this section, they captured a novel data set of 2,100 high resolution, high dynamic range indoor panoramas. Since network was trained on an LDR, low dynamic range data, it does not know about the intensity of the light sources. So they further trained the network on a novel data set of high dynamic range panoramas, which enables it to jointly reason about light source, direction, and intensity. They published their indoor HDR dataset on that link, and it's they also categorized their data. Since the light sources are not saturated in the HDR data, the network can be adjusted to directly learn the light source intensities instead of binary light mask. To do so, the network undergoes simple changes. They use target intensity value called T-int. T-int is defined as the log of the HDR intensity. Low intensities below the median of the training data set are clamped to 0, since they only care about the light sources. But in the unusual case where no pixels would be over this threshold, the ambient term item, you see on the top, given by the RGB, recovery should be enough to light the scene. So in case of that, like you couldn't get any light sources from HDR dataset, then you just use RGB, the ambient light, to relight the object. Finally, their render loss used for log intensity head is represented in the box as equation form. The L2 term on the intensity was added to reduce deconvolution artifacts. And then also they set it some weights. W1 set it 10, W2 set it as a 1, and the last 0.1. This is the result of HDR network. You see the ground truth log intensity on top left image, and the bottom left is predicted log intensity. On the right, ground truth RGB and predicted RGB, and the center is input. And you see they got very close. They got really good result, close to ground truth. Finally, this is the render result. So now we have rendered image with ground truth lighting condition and predicted lighting condition. And I would like to ask you to choose which picture is ground truth and predicted. Okay. Everybody agree? Let's see the result. Yeah. 가자. Yeah. Last one was the ground truth. All right. Next. See here. Okay. Let's see the result. Nah. No. Last one was ground truth. This is the last question. Why it's not moving? Whoop. Give me a sec. Okay. All right. I'll not zoom in this case. Left one. Yes, you're right. In the experiment section, they also rendered with using different method to compare with their results. Yeah, it's so bottom. You see left column, it's ground truth lighting with 3 different examples. And the second one, it's their HDR network results. And the third one, HDR network results, but they tuned intensity for this, so like suitable, to get the lighting condition for their object material. And on the right, there are related works. And they also conducted user study. Why it's not moving? Yeah. A/B comparison against ground truth lighting, and they conducted user study with 105 users with 20 scenes each users, and they got this result. And you see this is really the red bar representing user preferred the method, and blue bar representing user preferred the method and the ground truth equally. And you see the first one looks incredibly good. It says their HDR network results. And the funny thing is this one, their LDR network result, it's 도찐개찐. It just, okay. They did pretty good, I guess. But the HDR, obviously HDR, you can get the light intensity value. So like it looks more realistic, more than real object, I guess. So the conclusion is their main contributions, I can say, framing lighting estimation as end-to-end learning. And they generated new HDR panoramic data indoor scene. And they also created novel warping operator and render loss function, like tunable render loss function. That's all. And any questions, comments? Yes. Yes. No problem at all. Yeah. Before this one? Second one, this one? Okay. Ah. Mm-hmm. Mm. Mm. I wish I can contact Lalonde Professor Lalonde, to get this answer. Um, you know, if this the term of ground truth, it's representing the it's not the perfect ground truth. It's actually you have to do a lot of work to get the ground truth. Set the crumble, take the picture, high dynamic range picture with in the different angles, and then you make a panoramic image, and using that image to relight object. And in this case, they made an environment map through their network, and you have a different light position. So they could put the lights on the environment map. I think that's why it looks different. I don't know, I'm sorry. Yeah. Right. Yeah. Ambience lighting, reflections. Mhm. Mhm. Yeah. And in this case too, you see the shadow looks different. Hmm. Left one is ground truth, which is it has an ambient light also. So shadow looks kind of weak, but the prediction one looks very strong because there's the light placed on the top of the chair. And then the network just predicted lights, that lights is located on top of the chair. So yeah, looks strong. Any questions? Okay. Thank you for listening. Thank you.